You have to ID card? So this is actually so we have all this stuff that's so I needed it because Bob didn't have one.
Oh, yeah, right. Yeah.
See ya.
it did sound like super excited.
Hi, everyone. All right, let's wait for the typical 3 minutes. But before getting started, I just want to say I think I haven't shared yet the Zoom link for the office hour, which I'm going to do on Courseworks. There will be an announcement with the Zoom link for office hour. So we said Wednesday 2 to 3. So feel free to join. So that will be tomorrow. There was another thing. Actually a quick thing to check with Aiden. Aiden, I shared my lecture notes, not the ones from the class, but my handwritten ones. Did you happen to upload it already to Courseworks, or should I just do that?
So I believe I uploaded the
handwritten ones from the class.
Yeah,
from the class.
I think so. Yes.
Yeah, I'm just gonna also upload my notes, because there was a few parts where I just said things in words and did not actually write down notes. So that will be found then in these lecture notes.
Mm-hmm. Yeah.
Great. Are there any other questions that we should address? How's everyone feeling so far? Anything to let us know? You can also send messages offline, of course. But if there's anything urgent or anything we should discuss with the whole class, now's the time. It's like with Zoom, it's very hard to really connect very well. In the classroom, that's easier, but I hope you guys feel comfortable. Okay, so then probably time to get started. So actually today, from today on, we will have lectures by our TAs. And today is a very interesting day, because we're going to start also talking about Qiskit. And Aiden is going to give you an overview of the Qiskit platform and do some fun stuff with it. And I guess as in the last classes, we also do a break at some point. So I don't know exactly where's a good point. But time-wise, we roughly target 45 minutes, right? So it's 3:30 we try. Okay, great. Then I hand it over to you, Aiden.
All right, sounds good. Okay, let me just open up. All right. All right, so today will be like the first of many lectures where we'll be working like mainly with Qiskit. And then as for in the platform that we're going to be using is the Jupyter Notebook. So it's and it'll mostly be, the lectures will mostly be conducted in this format. So if you want to open up the lectures for review later, it's kind of necessary for you to have both Python and Jupyter Notebook installed. Yeah. So, well, yeah.
And yeah, we should say, if you have questions about how to do that, so these can be directed to our TAs, and you know, that should never be a hurdle to get like, you know, Anaconda going, or you know, get the work with Jupyter Notebooks going. So, yeah.
Absolutely. So do let us know, like, if you're encountering issues. There are alternative platforms as well. In the meantime, or in the short term, but we do recommend using Jupyter Notebook for submitting, like for lecture review, as well as submitting your homework solutions. All right, so let's begin. So for today, we'll be mainly doing a Qiskit introduction based on everything that we've covered in terms of gates from all the quantum mechanics, as well as like quantum gates introductions. And we'll be And the first experiment that we'll be learning to implement using Qiskit is quantum teleportation, which will also be covered. So just to provide some background on like what Qiskit is, it is what computer science is what like computer scientists call a software development kit. So it's a nice enclosed like package in Python that we will be using to perform like a quantum computations, utilizing like all the basic quantum mechanics that we understand in the language of what we call quantum circuits. And quantum circuits itself is a model for quantum computation that we largely borrow from the classical analog, in which a computation is a sequence of quantum gates or unitary operators on a n size qubit state. So that means a number when n refers to the number of qubits. So Qiskit was developed with the idea of utilizing IBM's superconducting circuit, and how all of these gates will be eventually implemented is on your physical like a so-called quantum computer. And IBM's version of the quantum computer is based on these things called superconducting qubits that is also called transmons. And what they utilize is the first two levels of a quantum enharmonic oscillator. So what you see here, if you just focus, so on the left is just a typical LC circuit, for example, that you have learned in class, where L refers to the inductor and C is a capacitor. And then in this scenario, you would have like a full harmonic oscillator where the spacing between your energy levels is all the same, which is equal to h bar omega in this scenario. So this isn't particularly great for like if you're trying to create a two-level system. So in the situation of a transmon, what it is that you have your little like superconducting material over here, for example, and it's put like in parallel with a capacitor. And what you get is that you generate an energy profile that looks like an enharmonic oscillator, where the energy spacings between all your different levels are slightly offset. And as we've covered in the introduction, our qubit system only focuses on the lowest energy state that we will refer to as the ground state, and the first excited state that we refer to as a one state, and like with an energy gap of h bar omega 0, 1 in this case. And any transitions from 1 to 2 will be detuned, because omega 1, 2 is smaller than omega 0, 1 over here. Yeah, and that's a reference for like for the paper where we got the diagram from.
Yeah, so we just want to say, really feel motivated to actually read about this, because that's actually where all the theoretical concepts we talk about really connect to reality, and it's exciting to actually know how things really work. And
absolutely,
try to cover some of this in the class, but since a lot of theory needs to be covered as they get going on the project, it's kind of time is limited, but really take the opportunity to talk to look into this. And that's also doing a paper or a project on the actual hardware. Literature review, for example, is another possible project idea.
Absolutely. And if you are intending on working for IBM in the future, this is a definite must-read review for you. Yeah, so just as another reminder, and there are two necessary packages in addition to Python. You do have to install Qiskit, and the installation instructions can be found on their website. And we do recommend installing Jupyter Notebook as well. Similarly, you can refer to the instructions. Do let us know if you have any issues. So let's just run some preamble. So I've installed both of those packages on my computer, and so just as a check just as a check, you should not be having any any error notifications when you run this. All right, so onto the lecture proper. So just as a recap, what we've covered, and we are going to be working mainly in the quantum information notation for today. So for the block split that we're using, we'll be describing it. We can represent our states in terms of 0 and 1, where the coefficient C0 corresponds to the complex coefficient or complex amplitude corresponding to state 0, and C1 corresponds to the complex amplitude corresponding to state 1. And as a reminder, we can write like these states 0 and 1 are just the shorthand notation for our column vectors, and any general state psi can be written as cosine theta over 2 of state 0 plus e to the I phi of sine theta over 2 of state 1. Right? And what the block sphere is that it's a very useful geometric interpretation of what a qubit can look like. Or looks like by transforming the complex numbers or coefficients in the imaginary plane. Right? Then this is the standard block sphere when we're referring to in the Qiskit or the quantum information notation, where our state 0 is on the north pole and state 1 is on the south pole.
Just to be very clear, this is exactly the same as from the last lecture. So, from now on, that is the block sphere for us.
Absolutely. Right. So just as a reminder, any point on the sphere is a possible superposition state of the qubit, where our poles represent the pure states or classical bits, if you want to think about it that way. And theta here, you can imagine as the contribution from each eigenstate, either 0 or 1, and phi describes the relative phase between the two states. All right, so we're now going to start visualizing how this actually looks like in Qiskit. All right, so in Qiskit, we use the quantum circuit object to store our circuits, and this is essentially the list of quantum operations on our circuit and the qubits that they are applied to. So for example, I'm just going to abbreviate the object quantum circuit as QC, and this one here means that we are starting our circuit with 1 qubit in this case, and so over here we set it to be 1, and whenever you initialize your circuit, all the states are always initialized in the ground state, or in this case, the state 0, right? Yeah, then and we can also use the initialize method to transform our state, to transform this into any state that we want. And we give the initialize method the vector that we want in the form of a list, and we tell it which qubit that we want to initialize in that state. So what we mean by that is, for example, if I wanted to define an initial state, for example, let's say in state 1, then I would do this as such, and then I will apply our method on our object, so which is QC dot initialize. You enter your initial state, then you enter which qubit number that you want to apply this to. So in this case, we're applying it to the 0th qubit. Then as part of Qiskit, you need to include some form of backend, and in order to get the output, you need to execute this. And you can and if I were to run this code, for example.
So actually, just to talk about the backend for 1 second, actually. So maybe you wanna say that right now this is running on a simulator, but you can also choose the actual quantum hardware backend.
Absolutely. Yeah. So right now we're running on a simulator, so we aren't actually running on a quantum circuit. But yeah. But it functions for the same purpose for pedagogical purposes, right? So in this case, if we initialize it in the 1 state, you can see that it matches our expectations as well. Now, if we were to change the different states, you can see, for example, the 0 state initializes it as such. And now if you wanted to do it as, like a 1 over square root 2, 0 plus I of 1, this is how you write it. So in this case, J over here refers to is the same as I, like notation that we commonly use. But yeah.
I think in engineering, the J is very typical, right?
Correct. Yeah.
So that's where they come from at IBM. It's a lot of engineers, so they pick J here. But the J is the I if you're more used to the complex unit to be denoted as I.
Absolutely. Exactly. Yeah, and then we can run it. Then you can see that it is on the positive y vector as we would expect, right? And similarly, if we were to take out this j factor, for example, then we would expect it to where will we expect it to lie on on Blocksphere, for example.
Aiden, there's actually one question that came just in. Is there a way we could access the Jupyter notebook now?
Not right now. I have not uploaded it.
Yeah, I think we should for the next lecture. Is a very good point. We didn't think about that, but I think that's what we should make available, so people can actually go live through the notebooks during the class also.
Yeah.
I think it's a very good suggestion. Thanks so much, and we'll try to make it happen from next class on.
Yep. I'll try to upload it during the break later.
Okay.
Later today.
Great. Thank you.
Yep. All right. Okay. So we've seen how we can, for example, initialize our qubits in a variety of states, but now we're going to actually apply gates to them to change their states and see how they evolve on the Blocksphere. So once again, as a recap, comparing between, as mentioned, quantum circuits are based on the classical analog, and similarly, quantum gates are also based on, they have similar classical analogs, which is sometimes called logic gates. So in the same way that we've understood for qubits, there are also classical bits, and with our superposition states, classical bits follow a Boolean logic. For X gate, that's a similar gate that is often known as a NOT gate, and this is how we represent an X gate, and that's how in classical computing, that's how they would represent a NOT gate, which in this case they'll sometimes call an inverter. Yeah, and for classical gates, they have their truth table over here, and you can see that it's very similar to how we represent it in terms of our 2x2 matrix for a qubit. And for the classical adder, what this means is that you're basically summing two numbers, A and B, like in binary. And you can also see that there is a similar quantum analog that we call a quantum adder that also adds that can also perform the same addition function over here. Yep. All right, so let's see some quantum gates actually being used. So let's assume that we initially start off in our one state, for example, and then let's see what happens. Let's see what happens when we start applying different gates to it. So, for example, if we were to apply the X gate to initial one state, I'll just pause for a couple of moments before I run this, but you can imagine you can think about what state this will actually correspond to on the Blocksphere. All right. So what do you expect?
Any answers?
Yeah, any answers? Yep, exactly.
Yep.
When you apply the X gate, you should spin up to the state 0 over here. Now, if we do a Y gate,
yeah, same question.
Yep. Similarly, you will find the vector at the 0, But now, if you look at this, there is a complex complex, in this case, j vector on our one state. Oh, sorry, like on our zero state in this case. For the z,
Again, question. Yeah.
Yep.
What do we get out?
we get a -1 as our phase factor on the one state. And for the S, and for the S and T gates, there will be.
So actually, just to say again about the Z gate, right? So we get a phase factor, but we don't flip the state because the rotation is around the Z axis. So that's just to recap really again. X gate means rotation around the X axis. Y gate is a rotation around the Y axis. And if our state is pointing to the north or the south pole, the Z gate is not doing anything in terms of flipping the state, but it changes the phase factor.
Mm-hmm. Yep, absolutely. Yep. So S and T gates are additional phase gates that we'll be going through like in a minute, but just to show you what they do. They add additional phase factors as well. For example, the S changes from 0,1 to 0i or j over here, and T adds a pi/4 factor in this case. And the Hadamard gate, which is H, puts it up into the -1 over square root 2, -1 over square root 2, and 1 over square root 2, 0, -1 over square root 2 for -1 over square root 2.
And here you see something that you will encounter a lot with Qiskit.
Correct. Yeah. So over here you see that the complex variable over here is non-zero, but what you also see that is an incredibly small amount. So it's e to the -17 over here. So and this is basically equivalently equal to 0. It's if you ever like work with numerical like computations before, you might have seen a similar phenomenon appear when you are trying to, I think, divide by very large numbers, I think. And this is just a numeric artifact, but what this is in reality is just approximately 0 over here, right? And this, as you might imagine, is approximately 1 over square root 2. Right? Yep. Now, if we were to try different initial states, now you can see that all the different, for example, the one state, you can see that it puts it in the 1 over square root 2 of the 0 plus 1 over square root 2. And you can see how, for example, the S gate in this case would, yep. So let me just initialize back into the original. And now we can apply S gate to this. You can see it forces it to make a pi/2 rotation. And if we apply it twice, you can see it just keeps rotating it about the z-axis. Now, if we were to change it to, if we were to originally start again, but we apply the T gate, then you can see it makes half the rotation, off your S state, for example. And if you were to apply our X gate, it doesn't rotate about the x-axis. If we were to apply the Y gate, it flips it about the y-axis and makes a pi rotation. If we were to apply the Z gate instead, originally starting from our same state, if we were to apply the Z gate, puts it in the same state, for example, in this scenario, Yeah, and lastly, we apply a secondary Hadamard, puts it into the 0 state. All right. Okay. So
Yeah, to familiarize yourself, it's good to play around with that yourself after the lecture.
Yep. Yeah. All right. So hopefully, like what we've shown you is like our so-called poly X, Y, and Z, which is the same as your X, Y, or Z gate, performs the rotation corresponds to an equivalent X, Y, or Z rotation, or rotation about the equivalent X, Y, and Z axis in the Bloch sphere, and hence that's where they get their names from. So hopefully like hopefully it's clear in this case that our X gate flips around the X axis, our Y gate rotates around the Y axis, and our Z gate rotates around the Z, or rotates our state around the Z axis in this situation. Yeah, and you've also seen their forms before, where this X corresponds to the X gate, this corresponds to the Y gate, and this corresponds to the Z gate. And also, and something that wasn't previously emphasized, but hopefully you've all seen this before, where this I refers to the identity matrix. All right. Yep. Yeah, and also like as a reminder of the additional single gates that you've used. For example, like for a Hadamard, which is written in this matrix form, like for a single qubit, in terms of 1, 1, 1, minus 1, with a 1 over square root 2 multiplicative factor. When you apply it to the 0 state, it transforms it into what we know as a plus state. And if you apply it again, then you get back to the 0 state. For the 1 state, it transforms the 1 state into the so-called minus state. And similarly, if you apply it again, you get back to the 1 state. All right. Just to show, if you were to initialize it in this state. Oops. Yep. For example, if you can apply the Hadamard. If you apply the Hadamard twice, it brings it back to the original state. So 2 consecutive Hadamards are equivalent to a identity matrix. All right. Yeah. So the additional gates that we will be mentioning, because you will be using it as well, is the T gate, where how you implement this, as shown, is by applying the T onto your quantum circuit, and then you insert the qubit number that you want to apply this to to replace the hash key over here. And what the matrix form for your T gate is 100 e to the I pi over 4 in this scenario. And then you might notice that, for example, 4 consecutive T gates would correspond to 1 Z gate, for example. Yep. So originally, just to show it again, this is our original state. Then if we apply a T gate in this case, you can see that it corresponds to an anti-clockwise rotation by pi over 4 over here. Okay. And the S gate corresponds to essentially 2 T gates, because e to the I pi over 2 is equal to I in this scenario. Similarly, if I were to apply, if this was our original state, if I apply our S state here by running it, corresponds to a pi over 2 rotation about the z-axis. Right? Let me know if I'm moving too fast or if you have any questions at any point.
Yeah, just sort of to summarize so far, we discussed in the last class some basic gates, especially the X, the Z, and the Hadamard, and now you see it applied in Qiskit, and then now you will see a bunch of other gates, or you saw already the S&T gate, which is basically gates that break down certain rotations into a formalized form, and we're going to continue a bit more, also basically finding a way to generalize rotations on the blocksphere. But basically there's sort of a kind of canonical set of gates that does pi rotations and pi over 2 rotations that we discussed also in the lectures before, and now we are going to introduce more refined gate operations, to kind of build a toolbox of stuff that's useful to put together interesting algorithms later.
Yeah. Absolutely. All right. So we are going to define this gate called the U-tree gate. And what it really is an arbitrary rotation gate. And it is aptly named the U-tree if you want to ever implement it, where you also need to include 3 additional variables, the theta, phi, and lambda, as well as the qubit that you want to apply it to. So what the form of this rotation is given by this matrix, where it's given by cosine theta over 2 minus ei lambda sine theta over 2, ei phi sine theta over 2 on the bottom left, and ei phi plus lambda cosine theta over 2. And what this really corresponds to is any arbitrary rotation about the Bloch-sphere. Okay. So and in practice, how this is implemented on a superconducting qubit is really as a series of Rx and Rz gates, which are so-called arbitrary rotations that will be discussed in the following slides. And this is how it's actually implemented in practice, like on IBM's quantum circuits, for example.
So here you put together a general rotation by assembling a series of rotations around the Z and the X axis. That's kind of similar to how you learned about rotations in 3D space using the Euler matrices, but here it's it's a little bit different because you're only on the hardware. You can only do rotations around the Z axis and the X axis.
Mm-hmm. Yep. Yeah. So up to this point, you've seen a couple of examples of like a special like quantum logic gates, like the NOT gate or square NOT gate and the Hadamard. And the reason why we're introducing these new gates is because we want to answer the question of what is the most general kind of quantum gate, like for a single qubit. And to address this, we must first introduce the family of quantum gates that are able to perform like arbitrary rotations about the 3 mutually perpendicular axes of the Bloch-sphere. So we've covered the Pauli rotation like matrices, so the X, Y, Z gates and the identity matrix. And then what it does is that it forms a complete set that allows us to define like any arbitrary rotation. So a U-tree gate is a combination of X, Y, and Z rotations at specific angles. So where these Rx, Ry, and Rz gates, you have additional control over what the angle in the block sphere that you want to rotate your quantum state to. Then we can thus build any complicated, like a single qubit gate or single qubit circuit, by using just these gates, the Rx, Ry, and Rz gates, as our basic building blocks. But in practice, this is further limited because the Ry gates, they have no physical implementation for any system like using electromagnetic waves or Rabi oscillations.
So yeah, just on that point, you remember from our discussions of Rabi oscillations that we discussed how the Bloch vector reacts as a function of electromagnetic wave shining onto it. Oh, you get to that. Sorry, yeah. I'm sorry about that.
Yeah, that's all right. Yeah. Yes, and then like if you recall, like from lecture 3, like we've written down like this like a Bloch vector oscillation, like in the physics term. Then you see that we have a cross product of our, like in our UVW, which corresponds to the XYZ, the similar to XYZ in the Bloch sphere. And then you can see that over here in this cross product, where this is a time evolution of the vector, right? You see over here in the y-axis, there's a 0 here. And what this really corresponds to physically is that there is no the Rabi oscillations cannot cause any form of rotation about the y-axis. And so what this means is that our y gates are not possible, like physically. Hopefully that's a bit clearer.
Yeah, thanks. Sorry for interrupting you before.
Yeah, no worries. Yeah, so and it really is like a motivated from the time-dependent Schrodinger equation. I'm not sure why I can't scroll down a bit. Yeah. So it's very motivated like from the time-dependent Schrodinger equation, where we have our where over here you can see the time evolution depends on the, for example, like the Hamiltonian time multiplied by time factor divided by the h bar applied on initial state in order to obtain our final state. And over here, you can replace like the ht factor with our original x gate and our rotation angle theta over 2, for example. And in order to obtain the Rx gate, you apply this. Yeah, you apply the x gate into our time evolution formula, and we obtain our following like matrices in this case. And you can see here that these matrices like might follow like more, or these matrices like give you the right Rabi oscillation factors to a global phase vector as well in this scenario. Yeah, so as mentioned, we can only apply Rx and Rz rotations easily. And our Y gates are done via a combination of Rx and Rz gates. And we will return to this in a bit. So where our Rx gate here corresponds to our like Rabi pulses, for example, if you want to set theta to, if you want to set theta equals to pi, for example. But in practice, we have full control over the full over the full theta that we can apply. And similarly, our Rz gate can correspond to our Z gate, our T gate, and our S gate as well. It all depends, and we have full control, and we can implement those gates just by controlling the time that we just let our states evolve in with time. And just purely according to the Schrodinger equation, our states will evolve with a phase e to the I omega 01t, where if you recall, omega 01 just corresponds to the energy difference between our two states. Yeah, all right. Are there any questions at this point? If not, I think it's a good time to just take a 5-minute break, and we'll continue in a bit. All right. While let me upload the slides now.
I have a question about the homework. I think there's a typo. Should I send an email about it or just ask it now?
It's best if you send an email so that we
Okay.
can forward to everyone. Yep,
Thanks.
no problem. All right. Okay. Hopefully everyone's back. All right, let's continue. Just give like one more minute.
I just sent the link for the office hour on Courseworks.
Awesome. Yep. All right. Okay, so we've covered all the single qubit states that we need to cover, or rather that we'll be using like for the rest of this course. And now we're going to look at the mainly two multi-qubit states, or two qubit states that you have already seen before actually, and that you've done in problem sets. So hopefully this is still familiar to you. So as mentioned, we are working in the quantum information notation. So where we can represent our product of two qubit states as a tensor product, and we will write it as such. So for example, if where this has been written before, for example, where this corresponds to the state, the amplitude of the state being in 0, 0, in 0, 1, in 1, 0, and 1, 1 over here. You might have seen a similar, like other examples that we use where we just write our A0, B0 as C00, for example, and C01, C11, sorry, C10 and C11 in other areas. And similarly, if you like for gates, you can write the tensor product of, for example, like two gates. If you're applying like a X gate in like for both states, like onto both for the qubit 0 and qubit 1, then you can write it as such, where the tensor product of two X matrices is given as this. And if you want to multiply this out, you get your 4x4 matrix that acts on our original state as such, our original 2-qubit state as such, right? Yep. So the CNOT gate is a shorthand term for a controlled NOT gate, and writing in the 0, 0, 0, 1, 1, 0, and 1, 1 state, where the first 0 is the control qubit, and the second 0, or the first qubit is, or the 0th qubit is our control qubit, and the first qubit is our target qubit, then our CNOT matrix can be written as such. And just to demonstrate an example implementation, this is how it would look like. For example, we will be using it very soon in a subsequent slide as well. So what if you actually flip the target and control qubits? For example, if we were to instead reverse the order, such that now our control qubit is qubit 1, and our target qubit is qubit 0. Then if you wanted to write out your matrix for your CNOT gate, you would instead change your matrix from our original, from our original of the 1, 1 and then 0, 1, 1, 0 in the bottom right corner into a matrix that looks like this. Right? And that's what happens if you flip the orientation. Let me know if you have any issues with this. All right. Yeah. All right. So how do you actually implement this on a superconducting qubit system? So this diagram is actually taken like from a paper, and the simple example is to just focus on the top half of the figure here. So in this situation, what you can imagine on figure A over here is that it describes the energy levels of the 4 different states. And what these 4 different states corresponds to is, for example, our 0 state refers to when both qubits are in the 0, 0. Our 1 state corresponds to when the target qubit is in the 1 state, but the control qubit in here is a 0 state. And our 2 state refers to the 1, 0 state, and our 3 state corresponds to the 1, 1 state in this scenario. So in order for a CNOT gate to actually be performed, what is necessary is that, for example, if you just imagine the target qubit from the 0 to the 1 state, so in the 0 to 1 state, the energy difference must be different, like for your target qubit, when your control qubit is in state 0 or state 1. And what you notice here is that between, for example, our 0 to 1 state here, when the control qubit is in the ground state, the energy difference is slightly different from state 2 to state 3 over here. You see? So in this case, we can implement our original CNOT gate by shining in, for example, light that is resonant with the state 2 to state 3. And what happens is that only if our control qubit is in state 1 does our target qubit actually make the transition from state 0 to state 1. If you shine in light corresponding to energy of 2 to 3, this means that if our control qubit is in state 0, then our target qubit does not see the light because the energy difference is off resonance. It's off resonant from 0 to 1. So it does not actually make the transition. And if this energy is sufficiently detuned, then it does not actually see the light. Does this make sense? Is this clear to everyone?
So there is actually one important comment. I think I try to ask questions that you may come up with, but ask your own questions. I just want to add some more comment to trigger maybe some more thought about this. So so one important thing here is that you basically use 2 qubits, but they have different resonance frequencies, right? One has a resonance frequency that is a little bit smaller. Goes from state 0 to 1, and then the blue one has a resonance frequency that's a little bit larger. Maybe you can point this.
Yeah, sure.
So
1 and 2 to 3. Right?
Yes, exactly. So you see, so the important part here is that not in this implementation, the 2 qubits are not identical. If they were identical, it would work. But there are 2 qubits that have different resonance frequencies, and then you can use the tricks of you can use this to your benefit, because as a function of the frequency for the microwave that you use, you can drive this 4-level system in a way that it effectively implements a CNOT gate.
Mm-hmm. Yep.
There's a question.
Yeah.
If you continuously apply omega 2-3, will the target qubit oscillate between the states?
So, hang on, let me close the chat so I can look at the view. Yeah. So let's imagine the 2 scenarios, right? So, for example, if our original target is in, for example, state 2, and then if our control qubit is in state 1, then this would correspond to as you exactly said, because it's a control operation. If our control is in state 1, this basically functions exactly like what we described in a Rabi oscillation, right? So you're exactly correct, where this would correspond to our essentially the Rx control Rx rotation around the Bloch sphere. But if it's in the 0 state, then this is where it's off resonant, where our light is off resonant. That means our qubit does not see the Rabi pulse. Then this will correspond to a simple a simple identity matrix where nothing happens, which is what you expect.
but it's really the important part is to realize in a real system a C0 gate you need the interaction between the two qubits, and that interaction shifts your resonances in a way that that basically the quantum state of one qubit influences the resonance frequency of the second qubit.
Absolutely.
And then when let's say the control qubit is in state 1, then your Rabi frequency to drive the target qubit from 0 to 1 has a certain value, or when your control qubit is in state 0, your resonance frequency to drive the target qubit is also is again different from control qubit to be in state 1. So but then once you have this in place, it's exactly as you're right, and as Aidan said, then you can start on any of these transitions, you can drive Rabi oscillations. And whether it's a C0 gate or not is dependent on whether your Rabi oscillation is actually running as, for how long you're actually applying the microwave. That decides whether it's a C0 gate or a more general manipulation on your 2-qubit system.
Absolutely. Yeah. So just to recap, is that in order to perform a C0 operation, you need some sort of like a controllable coupling, or like which we mean by interaction between both qubits, such that the energy difference in your target qubit actually changes if the control qubit is in either state. So, for example, if it's the energy difference between the 0,1 to the 0,0 is not the same as the energy difference between the 1,1 to the 1,0, for example, in this case. And then your pi pulse resonant at the energy of 1,1 to 1,0 will be off resonant and leave the target state unchanged if the control is in state 0 in this case. All right. Yep, and then this is the paper that illustrates it, or where this is implemented. Yep. Okay, and then the second 2-qubit state that we want to talk about is the swap gate, right? Where basically where this is the matrix for it. Very similar to a C0 gate, but in terms of the matrix form, but it swaps the 0, 1 and the 1, 0 state over here. All right. Yeah, and then this is how it would look like if you were drawing it, like in terms of the Qiskit, in terms of the circuit diagram, for example. And then this additional code is just to output the drawing in a much prettier form. All right, so let's start putting together our first circuit. And perhaps the first thing that we want to do is to start by entangling 2 qubits. So as always, the first stage is to initialize our quantum circuit. And in this case, we're initializing 2 qubits, hence there's a 2 over here. So qubit 0 and qubit 1. And then our first step is to apply the Hadamard gate to the first qubit, which we do by writing QC.H and 0 over here. And then we apply a C0 gate, which is a C0 gate where 0 is our control and our qubit 1 is our target over here. Yeah, and then and the combined output is given by this. So I'll just output the so let me just run this first, and we can talk about some additional details. And similarly, we're going to run this on a simulator and obtain our state vector and output our final state, which we see is given by this like a 4-element list. So you might notice that in this scenario, this corresponds to the 1/√2 of our 0, 0 state. and then 1 over square root 2 of the 1, 1 state. Yep, let's run this. Then there's a second way that we can see this, which is where we can, for example, plot the histogram of, let's say, of running, for example, like a number of measurements, and obtaining the probability of finding the state in our in a certain state vector, like of finding our of our qubit in a certain state. And over here you can see that we find them being both the 0, state and the 1, 1 state with half probability, which you might recognize, which means that our state is in like a 1 over square root 2 of the 0, 0 plus the 1, 1 state, which you might recognize this as being one of the entangled belt states that we've done last week. So I also wanted to make an additional comment about, for example, the inverted Qiskit notation. So what we actually mean by that is, let's say we just apply a Hadamard to our 0 state here. So in this case, you might notice that that in this scenario, then this would correspond to what we originally defined as our initial state being from like a 0, 0 to 1 over square root 2 multiplied by 0, 0, 0 plus 1, 0 in this case, if I recall correctly. Let me just quickly check. Make sure that we are keeping to the same convention. Sorry. Yep. So A0, A1. Sorry. So it's 1 square root 2 plus 1 over square root 2. Sorry. Yep. So in this case, it would, of course, Q0 is written as Q0, where this is Q0, and then this is Q1. And then originally, then this would be let me just check. Yeah, then in this case, then this will correspond to our state being in this state, right? But over here, you see that what we define as our, in quantum information, as our 0, 0, 0, 1, 1, 0, and 1, 1 state, right? What we see here is that when we expect half of the population to be in our first in our first elements and the third element, but you see here the output is in the first and the second, in the first and second row of our state. And this is what we mean by the inverted the inverted like a notation that you see in Qiskit. If we wanted to and if we wanted to see a similar example, if we were to measure the probabilities, you can see over here that our states are inverted in this case, whenever Qiskit outputs it. Does that make sense? So in quantum information, we write it as Q0 and Q1 as Q0 and Q1, but Qiskit, in this case, whenever you are printing things or plotting directly from Qiskit, the orientation is reversed. And we just want you to be aware of that whenever you are reporting your results. Okay? All right, let me know if you have any issues with this. All right. Otherwise, then we can go straight into the example that we wanted to go through, which is quantum teleportation. So the case here is that, let's say that so what is necessary for quantum teleportation to happen is, first we need 3 qubits, or like let's say Alice wants to transmit a qubit to Bob. Then what is necessary for Alice to do that, in addition to the qubit that she wants, is a classical communication channel, as well as an entangled photon pair where you send where one is given to Alice and one is given to Bob. So this is a situation that we have. So Alice wants to send send some arbitrary state. So let's call this state 0 to Bob, where our qubit has, can be some sort of has some arbitrarily defined amplitude in the 0 state and the 1 state. And in order to do this, you need 2 things. So first, you need 3 qubits. The first one is the qubit to be sent, which we call psi 0, and then an entangled qubit pair or a Bell state, psi 1, which we give to Alice, and psi 2, which we send to Bob. And then we also need a secondary classical communication channel. And this is a paper where quantum teleportation was done like through a 3 kilometer fiber. Yeah. So this is the full quantum teleportation algorithm or sequence, if you want to call it. So just to provide some insight in describing the big picture. The first section is just the initial preparation. So for qubit 0, that's a qubit that we want to teleport. We apply a arbitrary rotation state or a rotation gate U3 to get whatever state that we want to teleport. And then for qubit 1 and qubit 2, this sequence is you might recognize as this is just our entangling gate sequence, which entangles qubit 1 and qubit 2 in here. And then the next section is your teleportation sequence, where it basically transmits the information from qubit 0 to qubit 2 in this case. And then over here, we measure the states of qubit 0 and qubit 1 before applying corrections on our qubit 2, which is qubit 2, depending on the states that we measure, X gate or Z gate. And at this point, this is where the information encoded, or rather like our quantum state in qubit 0, has been transferred over to qubit 2 over here. And the last section is where we measure qubit 2 to determine that, to confirm that the information has been transmitted from qubit 0 to qubit 2, or teleported from qubit 0 to qubit 2 in this case.
Yeah, so that was something I just want to emphasize again. So the whole purpose of the circuit is to get the quantum state from qubit 0 into qubit 2. So you teleport the quantum, you don't teleport the qubit, but you teleport the quantum state from qubit 0 to qubit 2. And the role of qubit 1, as you see in the second step of the sequence, is to mediate a measurement. You do an operation. Okay, let me rephrase. In the first step, you entangle qubit 1 and qubit 2. Then you leave qubit 2 alone, but you use qubit 1 as a helper for you to transmit the information from qubit 2 to qubit 0. So you use the entanglement and the strong correlation that it comes with between qubit 1 and qubit 2 to get the information onto qubit 0.
Mm-hmm. Yeah. Right.
Sometimes I
So
just try to rephrase things in other words. So because some people, understand one explanation better than another. So it's just looking at the same problem from different sides. Sometimes it's very helpful.
yep. Yeah. Let us know if you need additional clarification.
Yeah, I mean, anytime, you're a bit worried you're so quiet. So
Yeah. All right. So perhaps like the easiest way to see what's actually happening is just to look at the math. Right. So in this case, we can write our overall 3-qubit state as the tensor product of our qubit 0 with our entangled photons, right? Our qubit 1 and qubit 2. So this is our original arbitrary state for qubit 1, and this is our Bell state for qubit 1, 2. So if we wrote out the tensor products, we can write it as such, right? Where originally the C0 divided by square root 2 is multiplied by, is given for the state 0, 0, 0 plus 0, 1, 1. And then you add this to state 1, 0, 0 and 1, 1, 1, where they have the factor of C1 over square root 2. Let me know if you have any disagreements about this. Yeah, and then the first step, if you recall from the original diagram, is that we first apply a CNOT gate with psi 0 being the control and psi 1 as being the target. And what this does is that this changes the state, not for the C0 state, but the C1 states, where if you notice, this switches the states from 1, 0, 0 to 1, 1, 0 and 1, 1, 1 to 1, 0, 1. Okay? Then the next step, if you recall, is that we applied a Hadamard on psi 0. And then what this does is that this, I think it's expanded out. Yeah, is that this changes our original state for our 0, 0, is that from our 0 state, it changes it to 0 plus 1, and for the 1 state combination, it changes it to 0 minus 1. And let me just zoom out so that you can see the full tensor product over here. Okay. And if you were to actually expand the full tensor product notation and actually calculate out what it was, you get a sum of 4 contributions in here. Let me just quickly go back. So you get a linear combination of 4 different qubits. The first is a 0, 0 and multiplied with a tensor product, where this is now our qubit 2 over here of the C0, 0 plus the C1 of the 1 state. Then you have a second, your second contribution is where the 0 qubit is in the 0 state, and the first qubit is in the 1 state, with a tensor product of the C1 in the 0 plus the C0 in the 1. And the third contribution is when the 0th qubit is in the 1 state and the qubit 1 is in the 0 state, tensor product of your qubit 2, which is in the C0 of the 0, minus C1 of the 1. And the last contribution is when your 0th and your 1th qubit are both in the 1 state, and then your qubit 2 has a minus C1 in the 0th plus the C0 in the 1st state. Okay. And what you really want in this scenario is to recover your original like a psi 0 state, which is your C0 and C1 in qubit 2. And hence, in order to do that, if you measure 0, 0, you just need to apply your I gate, which is to do nothing with it. If you measure 0, 1, So that means your qubit 1 is in the 1 state. Then you apply an X gate in order to switch these elements around, and then you recover your original state. And if you instead measure your qubit 0 to be in the 1 state and qubit 1 to be in a 0 state, you can recover your original state by applying a Z gate. And if you measure both to be in the 1 state, then in this case, you need to apply both the X and the Z gate in order to recover your original quantum state. And that's the purpose of the Z and X gates in this case. If you notice, if I were to just quickly go back over here. So over here, you measure the states of it. So over here, this is your entanglement protocol. And then you measure the states of your 0 and 1 qubit. And then you apply a conditional gate of X and Z depending on what you actually measure in order to get your final state. All right. Yeah, so Alice can measure qubit 0 and qubit 1, and then the Alice can send the information to Bob through a classical channel. And then Bob can apply the necessary gates in order to recover psi 0 and qubit 2. And something that interesting that you might notice is that at no point was there any operator applied onto qubit 2 directly. But yet, the state of qubit 0 was actually imprinted onto qubit 2. And then this is the point of quantum teleportation. Yeah. And it's an example of a phenomenon called phase kickback, which is a very commonly like a used tool to in many quantum algorithms in many other quantum algorithms out there as well. Yeah. So are there any questions at this point before we move into actually implementing this algorithm in Qiskit? All right.
Everybody fine?
Everybody?
You know, that's your chance. You can ask anything, you know. Even, you know, don't feel like you need to ask complex questions or something. Just anything that bothers you to understanding this is fine. No worries there, you know.
Yeah, even like fundamental like clarifications are all right too.
Any question is allowed about the lecture content. Okay, good.
All right, yeah, then if not, then we will proceed. Yeah, so as always, the first step is to initialize our quantum circuit. As mentioned, we need 3 qubits, so we are generating 3 in this case. And then we also need a couple of classical qubits, which is important because this is what we are actually measuring onto. So in this case, we need the Z and X qubit. So we need at least 2. The last one is just for like a confirmation whether like on our final state, just to show just to check and make sure that we're actually getting the state that the state that we're teleporting. Then we initialize our quantum circuit using this. All right. Then if you recall what the original diagram is, so the first step is to initialize our qubits. So right now, our 3 qubits are all in state 0, so we need to first prepare them. And so the first step is to generate our entangled bell state for qubit 1 and qubit 2. And we first do that by applying H onto number 1, and our control on our CNOT gate, with 1 being our control and 2 being our target, in order to entangle it and generate our bell state. And then the next step is that we can just to prepare Alice's state as some generic state. So for example, in this case, we are just preparing it in state 0 over here, and we are applying it onto qubit 0 over here. And you have a barrier for visual reasons. And then the next step is to apply our CNOT gate with 0 being the control and 1 being the target, before applying a second Hadamard on the 0 state. And then the next step is to actually measure the states, which we do via this measure method over here, where we measure the state of the 0, of the 0th qubit and the 1th qubit, and we save it onto our classical bit, which over here we refer to as we save it for the classical bit that we use for applying the Z gate, and a classical bit that we save for applying for using to apply the X gate over here. Then we can then apply the classical corrections, where we apply a condition where we only apply the X gate on qubit 2 if we measure the qubit, if we measure the qubit in the like for qubit 1 to be in the +1 state, or to be in the 1 state, and we apply the Z state, the Z state on qubit 2 if we measure qubit 0 to be in the 1 state. All right. Yeah, and then now we measure Bob's qubit to make sure that we did this correctly, which is given by this. Right. I think the diagram is not exactly correct, so let me just redo it.
Yeah, I think there was a doubling in the end, right?
Exactly. Yeah.
Yeah.
Let me just rerun it so that we eliminate that mistake.
Yep.
Yeah. And
Yeah,
this is
that's
how it
all.
looks like. Yeah.
Yeah.
Yep. And this is what we get. So just to recap: preparation, teleportation, conditional, and this is your conditional correction. And at this point, this is where our qubit 2 has our initial quantum state of qubit 0 prepared over here. And just as a reminder, you read this diagram from left to right. All right. Yeah, so now we can just implement the, Now we can just implement the full code. This is just copy, like this is just all the separate sections, like just all in one code block. And then we can, for example, run it for our state 0 over here.
Yeah, so what you changed here was just the angle in the U3 gate, right? That prepared our initial state.
Yeah.
So by changing so basically here, this used the U3 gate to make an initial state that is a completely arbitrary, that can be chosen completely arbitrarily. And here you just, choosing the 0 state.
Absolutely. Yeah, we'll try changing it like a couple of times. We'll try changing the state that we want to teleport a couple of times just to see like what the eventual output will be later. So let me just run this quickly. All right, and then similarly, we're going to run this with a simulator, and we're going to try this for different states. So right now, recall that we originally prepared in the 0 state. So what we expect to see for qubit 2 is that we expect to see qubit 2 being in the 0 state after we teleport it. And over here, we're just going to run it a number of times in order to get some probabilities, right? And over here, what you see is that you're going to have like somewhat equal populations in all of the 4, where over here, what you notice is, now recall that this is the Qiskit output. So this is Q0, this is Q1, and Q2, which is the first digit that you see. So that's qubit 2, which is the qubit that we want to teleport to. And what you see,
that is a quick thing. That was a question in my last class, right? The order of states in the cat, right? So here the histogram in the bottom is basically the cat, state cat. And here it's really indeed the first digit is the last qubit in the row. Yeah, just to recap.
Yeah.
There.
Yeah. So yeah, this is just Qiskit like convention. Yeah, so just so that you are aware, and so that you don't get confused when you're actually using Qiskit. But what you see over here is that our teleported qubit is always there. In this case, you always find that our qubit has been teleported and is always in the state 0 over here.
Yeah. And since the other two qubits can be in other states, you get a histogram with four bars here.
Yeah.
But when you add everything up properly, you see that there's unit probability to be in state 0 with the second qubit, or with qubit 2.
Yeah, absolutely. So now, what about another state then? How about let's do the simple cases. Like let's try, what value do I need to put in order to get state 1? I think it's theta equals to 180. Yeah, I'm not sure. Let's just try it. Probably not state 1 then. I think you need to put 360. Yeah, I think you need to put 360 degrees. Yeah.
Yeah, that's the definition of the U3 gate. Yeah, actually, it's yeah. Okay, good.
Yeah, probably need to pull out the definition one more time.
Yeah.
Yeah. So let's just quickly scroll up and have a look. Okay. In order to change it into the state 1, I need my theta to be
Actually, you need a phi, I think.
yeah, I need phi.
Yeah.
Okay, this is not as simple as I originally expected it to be.
Yeah, but maybe you can replace replace the U3 with a rotation around X, right?
Yeah, that's probably the easiest way to do it.
I think we'll do that.
Yeah, so let's just simplify this, and let's just do qc.x qr 0. Yep.
So you see some live here, so that's good. Sorry.
Point. Yeah, so let's say we apply x gate, then we see that we have changed it. We've changed it into the 1 state, for example.
Nice.
All right. Similarly, you can do additional rotations to this. Let's do a H Hadamard gate. Then here we see that now it's put in this equal superposition of the 0 and the 1.
Right, and we should emphasize that the output here is a histogram of probabilities. What you cannot measure with the classical qubits is the phase information, right? So you don't actually know. So initial qubit is now 1 over square root 2 0 plus 1 over square root 2 1.
Yeah.
But it could the same histogram you will get if you have 1 over square root 2 0 minus 1 over square root 2 1. Because the probability is not sensitive to this.
Absolutely. And then you can verify yourself by adding, like an additional phase gate, for example, a T gate.
Right.
And then you can, where now you apply H and a T. And then if I were to run this, you still cannot tell anything about the relative phase between the 0 and the 1 gate in this case. Yeah. So teleportation, it does teleport the state, but when you're actually measuring it, you're unable to extract it just from the actual phase difference directly just by measuring the state. If you wanted to do it, you would need to, for example, apply additional basis transformations in order to actually see it. All right.
It's something for you to think about, what you actually would have to do before the measurement to differentiate the state 0 plus 1 divide by square root 2 and 0 minus 1 divide by square root 2.
Yep. And yeah, but that's it. That's it for the quantum teleportation. So in summary, what you need is 3 qubits. You need 3 qubits, and you need one pair of them to be entangled, as well as classical channels in order to save your results and send it to and send it between your two parties, like from Alice to Bob. So because of the classical channels, if you recall from Bell's inequality, this does not like violate anything about like a locality either. So because like you can only transmit the information like with like as fast as the speed of light through your classical channels. Yeah.
Yeah, so this attaches a little bit, actually in a concrete way to the EPR problem, where basically Einstein and his colleagues suspected that with entanglement, you could actually, get information transfer faster than the speed of light, but that's not true, because to actually teleport a state, you still need a classical bit. And the classical bit you can only communicate to the other to anywhere with maximum speed of light. So everything is kind of saved. Information cannot travel faster than speed of light.
Absolutely. All right. Are there any questions at this point? Yeah. Otherwise, I think it's actually a
perfect timing.
Yeah, it's a good time to stop actually.
Yeah, very good. And just it came from me like from a fire hose on the courseworks. I sent a couple of emails. I will send another one about implementation of quantum teleportation using photons. And that was actually the first demonstration of quantum teleportation using photon polarization states. You will see it's a paper that I wrote myself as an undergraduate. And apologize the English of the paper. It was before I was ever in an English-speaking country. But yeah, I hope you still enjoy the paper. It's quite comprehensive. So I'll send that, and we'll see you soon again at the office hour tomorrow or on Thursday. Bye-bye.
Thank you, Professor.
Yeah.